This video, we will go through what FPGA can do and how it is better than Breadboard. We'll explore the process of prototyping a digital circuit, taking an idea from design to a working model. To demonstrate digital circuit prototyping, let's start with a fundamental building block, the binary counter as an example. A binary counter is a digital circuit that counts in binary numbers. Instead of counting 0, 1, 2, 3, like we do in decimal, it counts using only zeros and ones. It counts in binary like 0, 0, 0, 1, 1, 0, and finally 1, 1, and it repeats in same sequence. Let's build a digital circuit for our 2-bit binary counter. This is JK flip-flop based ripple counter. Each time the clock signal pulses, the counter increases its value by 1. Here, the JK flip-flop in brief is a type of bistable multivibrator that has two inputs, J and K. The behavior of this flip-flop depends on the combination of these inputs. In our case, we have tied the input to logical 1, and in this condition, it will toggle between two states, 0 or 1, with each clock pulse. The output of one flip-flop becomes the clock input of the next. This creates a ripple effect, where each flip-flop changes its state one after the other in response to a single clock pulse. The first flip-flop, the least significant bit, toggles on every clock pulse, and its output is the first bit of our binary count. The second flip-flop, the most significant bit, only toggles when the first flip-flop changes from 1 to 0, creating a ripple effect. The outputs Q0 and Q1 will have values 0, 0, 0, 1, 1, 0, 1, 1, and comes back to 0, 0, and then it repeats in same fashion sequentially. Now that we've discussed how the JK flip-flop-based ripple counter works, let's move on to the exciting part, building and testing it on a breadboard. A breadboard is a tool used to build and test circuits without soldering. It has rows and columns of conductive metal strips, which are arranged in a grid, allowing you to easily place and connect electronic components. The rows are generally divided into two sections, one for power, positive and ground, and the other for connecting the components together. Let's build this circuit on the breadboard. We have used a switch that behaves as a clock pulse, and two LEDs which will glow when the outputs are high, and we are using CD4027 IC for two JK flip-flops. Let's power up the circuit using 9-volt battery. We will now give one clock pulse to JK flop by pressing the switch button. LED 0 will glow, and giving us the first count transition from 0, 0 to 0, 1. Let's press the button again. We got 0, 1 to 1, 0. Let's press again. We got 1, 0 to 1, 1. Finally, LEDs will turn off, returning to initial count state 0, 0. I found the circuit reference from hackday.io. Please check it out to know more about this circuit on Breadboard. The link is available in the description. One of the most popular and educational examples of this is the 8-bit CPU, built by Ben Eater, a YouTube creator who has made an entire series on how to build a simple 8-bit computer from scratch, using breadboards and logic components. Please check out his video. I have video ink available in the description. While building an 8-bit CPU using traditional breadboards and logic components is an amazing learning experience. Using an FPGA, field programmable gate array, can simplify and speed up the prototyping process. FPGAs are reconfigurable chips that allow you to program them to perform specific tasks, such as emulating digital circuits like a CPU. Using an FPGA makes prototyping your CPU faster, more flexible, and more scalable, helping you bring complex digital designs to life with less effort. But FPGA is just a chip. We need LEDs and switches to interact with it. So, we have FPGA boards. This is an example board with LED and switches now. Let's build the same binary counter using FPGA. With FPGA, we will be able to build any digital circuit we want, but we don't do any physical connections. We will just write a code for the circuit we need, using hardware description language HDL. There are many HDLs available. Here we are using System Verilog code, and this is the code for 2-bit counter. This code will create a 2-bit counter in the FPGA. In this design, 2-bit counter circuit for the FPGA was created using D flip-flops, rather than the JK flip-flops used in the earlier breadboard-based design. This is because the flops available in the FPGA is D flops, although the underlying functionality remains the same, counting from 00 to 11 in binary, equivalent to decimal values 0 to 3. Let's power on the FPGA board. You see nothing happens, because FPGA is not programmed and now it is like an empty breadboard. To get our design onto the FPGA chip, we follow a specific workflow like synthesis, PNR, and program file generation. In synthesis, with the help of tool provided from FPGA vendors, we will be able to convert our HDL code into a digital circuit using the specific logic resources available inside the given FPGA. In implementation, also known as place and route, PNR, the tool virtually maps the synthesized logic onto the locations on FPGA's internal fabric, and then perform the connections between the components, also known as routing. The connections will use the routing resource, which is already present between these components. Program file generation. After successful implementation, tool creates a programmable file for FPGA that we dump onto the FPGA. Once programmed, the circuit is realized instantly within the chip. To illustrate it further, I want to show it with Ultra's Quartus Prime tool, since we have Ultra FPGA board. Once you create a Quartus project for our 2-bit counter, you will see on the left corner the workflow analysis and synthesis, which will do the synthesis, fitter, which will do place and route, assembler, which will generate the program file. There is other process like timing analysis and EDA netlist writer, which can be discussed in more detail in future video. Let's understand analysis and synthesis. This will invoke the synthesis process, which converts our HDL code to digital logical circuit using FPGA resource. In the synthesis first, it will create a digital logical circuit using HDL, and it is called generic mapping process, or even called as elaboration. Here it will use basic gates and flops generically. Next, it will perform a technology mapping. Here it will replace generic components to FPGA elements like lookup tables, LUT, flops, buffers, etc. We can discuss in detail in future videos on the resources of different FPGA from different manufacturers like Xilinx, Ultra, Lattice, etc. Let's move to fitter, which will perform our place and route operation. The chip layout of FPGA will already be aware by the tool as per the device we have selected in the project. Then it will take the circuit from the synthesis stage and will start performing the mapping of the components onto the device virtually. The layout of FPGA is more complex to explain in this video. Maybe I will try to explain in another video in future. As we zoom into this layout, we can see the logical resources or logic elements, and also the routing resources that connects these resources. So, here we can see among the thousands of logic elements, approximately 2,900 logic elements, our counter design just occupied 2 logic elements, and this is around 0.06% of the total logic elements for this family of FPGA. So you can see the advantage of FPGA over the breadboard implementation here. If we further zoom in, we can see the lookup tables and registers for which our digital circuit is mapped and routed. The synthesis and PNR require many inputs files along with our HDL code, which can constrain the design for power, area, and performance optimizations. I am happy to make one more video fully dedicated to it in future. Now, let's move further into generating program file for the FPGA. After doing the successful PNR, the tool will be having the details of where to enable LUT register and routing resources on the FPGA chip. This information will be encoded into a binary file. We will be dumping this binary file from our personal computer into FPGA board to realize our intended circuit in the FPGA. The assembler will generate this binary file, also known as programming file for the FPGA. For Ultra FPGAs, it is called .sof file. To program the device, we need to select the Program Device option. We use USB Blaster from Altera to connect the board to our personal computer. Once we enable programming from the Quartus tool, the programming file will be dumped into FPGA. Now let's test our binary counter. Currently, I will assume the board is given reset already, and counter is in initial state 0, 0. Now, as we press the button on the board, the counter will increment to next state 0, 1 from 0, 0, and LED 1 will glow. As we keep pressing the button, the counter will increment like before, and making LEDs to glow according to counter logic. If you have come this far, if you have liked this content, please feel free to like, subscribe, and share our video. You can find multiple FPGA boards from multiple FPGA chip manufacturers like Ultra, Xilinx, Lattice, etc. So, where I can use FPGA. We can use it to build the complex design where we expect quick response. On 20mm by 20mm FPGA chip, you can have very complex digital circuit compared to a breadboard, and you can prototype your ideas very quickly. But how FPGA is different form processors like microcontrollers or GPUs. A processor work on a flow of fetch, decode, execute, instruction by instruction, and the hardware for processors are always fixed. FPGA, on the other hand, are like polymorphs at hardware level. You can change it to anything you want at the hardware level and build your design like Lego bricks. You can make a custom small processor of your choice or multiple of these small processors. Or you can build a crypto mining engines, or it can work as reconfigurable signal processor for communication system inside the satellite, or anything you like it to be, even for inferencing a neural network. But there are limitations. The learning curve is more compared to programming a MCU or any processor. And also the FPGA dev boards are 2 to 3 times costlier relative to MCU dev boards. And also, we cannot do everything with FPGA, like building Intel i3 processor or GPU on a single FPGA, because it will not have that many resources available in one FPGA to fit these modern processor design. But we can prototype them at lower operating speed using multiple high-end FPGAs. In Intel or NVIDIA, they also use FPGAs to prototype their design before building the actual ASIC chip. They call it pre-silicon prototyping and verification. They use multi-FPGA boards, for example, HAPS and ZeBu systems from Synopsys. That's all for today. I am planning a deep dive video in future as per response to this video, and will adopt the contents according your feedback from the comment. So please comment. And if you like this video, please hit a like button and subscribe button. If this video has helped you to understand the FPGA, please share it with others.